Alright, so we'll continue with our discussion on electrochemistry. This is now the third part. So in here we'll discuss about the standard reduction potential. So remember, in a galvanic cell or in a electrochemical cell, like in the figure here, in the given figure here, remember that the electron flows from our anode to our cathode. So this is due to a difference in electrical potential energy between the two electrodes. And this current is actually measured by our voltmeter. So this is actually measured in volts. So basically the measured volt, that is the overall cell potential. So this is the E cell. So this is the overall cell potential, meaning for the two half cell reactions. And this varies with concentration, temperature, and of course the metals or the ions that are used. So we define in a certain conditions the cell potential as the standard cell potential. So there is a standard cell potential. So this measured according to certain standard state conditions, which we will define. Okay. The standard cell potential. This is the cell potential under standard state conditions. So the standard state conditions that includes the concentration of our ions. So that is in 1 molar. And then the temperature is actually the temperature at which the reaction is carried out is 25 degrees Celsius, and then the pressure is actually 1 atm. So this is the conditions, no, at standard state. So when you see um, values as standard reduction potential or standard cell potential, so this is carried out in this standard state conditions. So remember that each of the half cell can be considered a reduction potential, which is, of course, no, there's an associated reduction potential with it. So this measures the natural tendency of the half cell to proceed as a reduction. So each of the half cell, there is a standard reduction potential, okay, or what we call as the E red, no, E not red. So each of the um, each of these half cell has an associated standard reduction potential. So when these two half cell reactions are connected, of course, what happens, the more positive or larger standard reduction potential, that's the half cell potential, that's the half cell that will actually undergo reduction. And then the other one, meaning the less positive half cell, that will actually undergo oxidation. So what we can actually measure basically is just the E cell. Okay, so in other words, our E cell, this is just the summation of the two potential, meaning in the two half cell reactions. So we have the reduction, and then of course in the oxidation, meaning the reduction potential associated with our cathode and the potential associated with our anode. So what we can measure is just the E cell. So the question is, how do we get the standard reduction potential or the oxidation potential? So what we do is we select a specific half cell as our reference or defined as the zero. Okay, and then use this one to get the standard reduction potential for all other half cells. So again, to measure the standard reduction potential of any half cell, so we select a specific half cell as our reference, which we define as 0. So there is a reference half cell which by definition, so this has a cell potential of 0. So then we compare it with the other half cell reactions. So our reference half cell is actually what we call as our standard hydrogen electrode. Okay, so again, this is carried out at standard state conditions, which I've already described earlier. The concentration of our hydrogen or HCl is 1 molar, and then the concentration of the pressure of our gas is at 1 atm. And this is the equation: 2 electrons plus 2H plus forming hydrogen gas, and this is defined to have a zero potential. Okay, so how do we measure then the reduction potential of other half cell reactions? So again, we measure the charge on the electrodes, meaning in both electrodes. So in this case, we have the zinc electrode, and then we have, of course, our standard hydrogen electrode as our basis. Okay, and then we get the sum, no, of the overall cell potential. That's the sum of the reduction potential at the cathode and then also at the anode. So to calculate our E cell, we have the formula, the potential at the cathode minus at the anode. So initially the formula we said earlier is we simply add, right? But remember, the reduction potentials, which you will see the table later, these are all in reduction expression or reduction reaction. So when you reverse, so that will be the oxidation. So the sign will be changed. Okay, so that will not change anymore the sign. So when we reverse or inverse the reduction equation, so that will not change the sign anymore. So we'll just change we'll just make the potential of the anode negative. So the formula now is the E cell is equal to the E of the cathode minus E of the anode. Okay, so again, once the half cell potentials are determined, so we can always calculate our E cell. Okay, and if the other one is defined as our standard, meaning our reference, our 0, so we get we can calculate the reduction potential of a particular half cell. So for example, here our zinc, the reduction equation is zinc 2 plus to zinc solid. Okay, so to get here, so again we have this assembly, we construct our galvanic electrochemical cell, and then we measure the overall cell potential. So again, the hydrogen is considered 0 here. So that's around 0.76. Okay, so that would be negative 0.76. So just directly substitute in the formula. E cell is just equal to our hydrogen, so minus the cathode. So just rearrange this. Okay, so cathode minus anode. At the cathode, it's 0, and then at what we're trying to calculate is the anode. Okay, so the same thing, no? Another example is the reduction potential for your copper. So if you notice here, the hydrogen now is at the anode, okay, and the copper is our cathode. Okay, so again, we still get the difference, the same process. So we get the E cell, so we can determine the reduction potential at uh, at our cathode, meaning the copper electrode. So the standard reduction potentials of all the other half cell reactions, basically it's summarized now in this table. So if you look at the table, this is the potential for the reaction as written, meaning in all of these are in reduction equation. So remember, so what I've said earlier, the more positive the cell potential, the more positive the reduction potential, meaning the greater the tendency for the substance to be reduced. So in other words, the more positive, more likely to be reduced, so better oxidizing agent. So we have the oxidizing agent on the top here. Okay, so increasing ability. So the more negative, meaning the better reducing agent. So when you compare the two half cell reactions or values, the more positive will undergo um, reduction because it will function as an oxidizing agent. Okay, these half cell reactions are reversible, so you can reverse it. So usually when you reverse, the sign will be changed. So if it's positive, then it becomes negative. And then of course the sign, as what I've said, the sign of this potential changes when the reaction is reversed. So when you make it an oxidation, so from the positive it becomes negative, or if it's from negative it becomes positive. And then changing the stoichiometric coefficients of a half cell reaction does not change the value of our reduction potential. So regardless if it's the coefficients of our, let's say, copper, we have 2, and then our zinc is 2 also, so it will not have an effect. So the cell potential or the reduction potential is still the same. So using the standard reduction potential, we can determine, we can predict the redox reaction. So when we connect the two half cells, we can use the values of the reduction potential for each of the half cell again to predict the redox reaction. Remember that the half cell reaction with more positive, meaning it will undergo reduction, and the other one is oxidation. And then if the overall cell potential is positive, so if the overall cell potential is positive, that means that it is an spontaneous reaction. Okay, so we can use the values here. The more positive, it will undergo reduction. Okay, so let's take a look at this problem. So what is the standard EMF, meaning the overall? What is the standard EMF of an electrochemical cell, meaning the overall cell potential? Okay, so the E cell standard. Okay, made of a cadmium electrode in 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium nitrate solution. So the reduction equation and the potential, corresponding potential, is given here. Okay, so remember, the more positive, so that will undergo reduction. So that's a better oxidizing agent. So the more positive here is, of course, no, the cadmium. It's negative 0.40 compared to negative 0.74. So cadmium will undergo reduction, and our chromium will undergo um, sorry, cadmium will undergo reduction, and then the chromium will undergo oxidation. Okay, so what will happen at our anode? That's oxidation. So that is the oxidation of our chromium from 0 into chromium 3 plus, which is oxidized by cadmium. Okay, then to balance the equation, we have 3 electrons. And then at the cathode, we have the reduction. So 2 electron plus cadmium 2 plus, forming cadmium solid. So to balance the equation, make sure that the electrons lost and the electrons gained are the same. So remember, in the anode or in the oxidation, the electron is in the product side because it means loss of electrons. And for the cathode, since it's reduction, that is brought about by gain of electrons. So the electron is in the reactant side. So to balance, so you multiply, so there's a multiplier, so you just get the LCM of the two magnitudes, meaning the smallest number that can be divided by both this magnitude. So 3 and 2, the LCM is 6. So 6 will be the total electrons lost and the total electrons gained. So to make this 3, 6, so we multiply the whole equation by 2, and the other equation we multiply by 3. So that will give us this resulting equation. So the 6 electrons, will be cancelled. So this becomes 6 electrons, right? So that will be cancelled, and 2 times chromium, and then 2 times chromium 3 plus, and then 3 cadmium 2 plus, and then just distribute 3 cadmium. So we have this overall equation. So to get the overall cell potential, the standard cell potential, so again, the formula is the cathode minus anode. So it's already negative. Remember, it's already negative. So here, it means that we don't need to uh, reverse the sign of our potential for the oxidation. Okay, so in other words, the values here, you take the values as reduction potential. Do not inverse anymore, because if you look at what will undergo oxidation is chromium, right? But this is reduction. So when you reverse this, it becomes positive, right? But we already changed our equation, so we already reverse, okay, by making it a negative, so instead of positive. So remember, earlier we said the overall cell potential is just the sum of the cathode plus the anode. But since we need to reverse uh, the equation for the anode because it's oxidation, so instead of reversing it, we just have the negative, or it's already inverse in the formula here. So in other words, we simply use directly the reduction potential. So E cell, that's negative 0.40 minus negative 0.74. So that gives us 0.34 volts. Okay. And then another important um, effect of the electrochemistry or application of electrochemistry is we can actually determine and relate, we can determine the potential to the capacity, of this redox to perform work. So we define the delta G. This is the maximum useful work that can be obtained from the potential, meaning from the redox reaction. So in a galvanic cell, the work is supplied by the electric current. Again, it's meaning moving electrons through wire. So we define the maximum work with this formula. Delta G is equal to negative NFE cell. Okay, this one. Okay. So if it's a standard state, so the same thing. So the standard delta G gives free energy. So the N here stands for the number of moles of electrons in the reaction, and then F is the Faraday's constant. It's 96,500 joules per volts mole. Okay, or of course remember joules over volts is just equal to coulomb, 96,500 coulomb per mole also. And then at this point we can also introduce the equilibrium constant. Remember this topic. So we represent the equilibrium constant as K. So the Gibbs free energy is related to the equilibrium constant K in this equation. Delta G is equal to negative RT ln K. So when we rearrange it and equate it with our when we equate this with this expression and rearrange it, so we can get the E cell. Okay, which is the formula. E cell is equal to RT over NF times ln K. And then of course the sum of the constants. So because this one is standard, so that's the symbol of the standard state. So the R is remember the gas constant, 8.314 joules per k mole. Then temperature is in 298 Kelvin, meaning that's 25 degrees Celsius. And of course the F, that's the Faraday's constant. And then of course you cancel, no? So we get this shorter, simpler expression. So 0.0257 volts over N over 0.0257 volts over N ln K. And then we can convert that natural logarithm to log. So from ln, that is converted into log, so it becomes 0.0592 volts over N log K. So actually either. So this is the expression relating our E cell to the equilibrium constant. Okay, so in other words, the cell potential that's related to our delta G, the capacity to it's a measure of the capacity to do work, and then of course our equilibrium constant. Okay, so remember this expression, delta G is equal to negative RT ln K, and that's also equal to negative N the cell. Okay, so let's have this problem. What is the equilibrium constant for the following reaction? So we have the equation. Again, this is just very straightforward. It's just direct substitution. So first, based on the table, the reduction potential, so you get the values. Okay. First is important is to determine the n. So you balance the equation. So in this particular problem, the n is equal to 2. And then from the equation, you would know that what is being oxidized is our silver. So the oxidation equation is silver, forming 2 silver plus, and our reduction equation is for the iron, because the iron is converted into, from iron 2 plus, it's converted into iron solid, from 2 plus to 0. So our cathode, this one, and then our anode, the reaction, the silver plus to silver. Okay, and then you get these values. Again, this is our cathode, this is our anode. So you get these values from the table, the standard reduction potential table. So that's a negative 1.24 volts. And then just substitute here. Okay, and then n is equal to 2. So you can rearrange so that you can get the k. So it just E exponent E cell times n over 0.0257. So you can use your calculator, just directly substitute. So we get a value of 1.23 times 10 to the negative 42 as our equilibrium constant. Okay. So another important consideration or consideration about spontaneity of redox reactions. Earlier, that's under conditions at the standard state. Okay, so this time is under conditions other than standard state. Okay, so if it's standard state, that's how you will do, no? So you can easily calculate the equilibrium constant. It's related to the overall cell potential. For conditions other than standard state, the concentrations of the half cell species affect the E cell. So remember our standard state condition, the concentration of ions is 1 molar, and then the pressure of the gases, it's 1 atm, right? So if the concentrations are not in 1 molar and then the pressure is not in 1 atm, the potential actually changes. Okay, so that's the effect of changing the concentration or the pressure. So what we will discuss here now is the spontaneity of redox reactions under conditions other than standard states. Okay, so we have this equation, delta G, meaning this is the not in a standard state. So delta G overall is equal to delta G naught standard state plus RT ln Q. Q, this is just the expression of the given concentrations of the species, similar to our K. Okay, so we equate with our with the formula negative NFE and also the standard state, and then we directly substitute here. Okay, here here and here, so this one will substitute, so we get this expression. Okay, so this will give us, and so we rearrange, so you rearrange this, so this will give us what we call as the Nernst equation. So we use the Nernst equation for conditions other than standard state. Okay, meaning again the concentrations of our ions are not in 1 molar, and then the pressure is not 1 atm. So we can rearrange this one, and this gives us the Nernst equation. So the Q, remember, so this is the concentration of the products over concentration of reactants. So you had covered that in your senior high school, the equilibrium expression or constant. So it's just the ratio of the concentration of your product, so that is molarity over the concentrations of the reactants. Again, that's also in molarity. Okay. So if the temperature is at 25 degrees Celsius, meaning 298 Kelvin, so we can simplify further the Nernst equation. So this becomes E is equal to the E naught, or the standard, potential minus 0.0257 over n ln q. Or in log, it's E is equal to E naught minus 0.0592 over n log q. Okay, so actually either. Or we can use a log, no? So usually log is being used. Okay, so let's apply that in this problem. So will the following reaction occur simultaneously at 25 degrees Celsius? So the concentrations are given, and then also the equation, the redox, the balance equation is already given. Okay, so at the oxidation, we have cadmium. So from 0, it becomes cadmium 2 plus. And then our reduction is our iron 2 plus is reduced to iron solid. Okay? And then you balance the equation. So the N here is equal to 2. And then we get the standard cell potential. Our E cell is our cathode, this is our anode. And then this is from the table, from the standard reduction potential table. So the standard cell potential is negative 0.04 volts. And then we use the Nernst equation. So E naught minus 0.0257 over N ln Q. So our Q would be, because we don't include the solid in the expression. So just the ions. Okay, so our Q is just the concentration of cadmium 2 plus over the concentration of iron 2 plus. Okay, so we exclude the solid. It's part of the constant. So we have the Nernst equation here, okay, to get the cell potential, which gives us a value of positive 0.013. So what's the meaning of this? So will the reaction proceed spontaneously? So remember, if E is greater than 0, then that is spontaneous. So meaning the reaction here will proceed as written. So if E is less than 0, so that is non-spontaneous.